Hello, this is Dr. David Kreller of the Department of Chemistry of Georgia Southern University. I'm here with a video that is hopefully going to help you understand how quadrupole mass filter works. So the quadrupole mass filter has an anatomy or physical sort of layout that looks a bit like this. There's four parallel rods. Rods are actually electrodes. They have electric voltages applied to them, and then because of those voltages, electric fields that go out in space around them. Now, ions that have been generated in some ion source are kind of manipulated so they travel down through the rods, in the space between the rods. This is a rather simple construction, but there is something complicated about this whole thing. The complicated part is not physically what it's like, it's just simply these four rods, so that's pretty easy to... The complicated part is the voltages that's applied to them, and hence the electric fields that are associated with those voltages. Now, so those voltages are complicated in the sense that they have two components. So each rod has on it a direct, constant, and alternating portions of voltage. Now let's get a little more specific about these voltages. Okay, so each pair of rods is connected. Any rod has the exact same sort of voltage profile. The exact same thing is happening to the voltage of the rod directly across from it. Two rods have a voltage, say the DC voltage is positive, and added to that is this alternating voltage. For the other rods, it's a negative DC voltage. Also, the alternating voltage is, of course, alternating, but because it's got this negative sign out here, it's 180 degrees out of phase. So the alternating voltage on one pair of rods is 180 degrees out of phase with the alternating voltage on the other rods. Ions, as they're going down through this central area within the quadrupole, they're affected by the fields because, of course, the ions have a positive charge on them, and so they're affected. In any given time, if the ions are sensing a negative field, they'll be attracted in that direction towards that field. And so ions, basically, they either make it through this filter and they're detected by this ion transducer, or they do not make it through the filter. Only ions of a specific mass charge ratio make it through the quadrupole at any particular time. Whether an ion makes it through there depends upon the magnitudes of the DC and RF voltages at that given point in time. So here's what happens to these voltages over time. Over the course of a certain time period, both the DC voltages and the amplitude of the alternating voltages increase. And they kind of increase together in lockstep. As they have a certain ratio, but they increase in lockstep, so the ratio of the two stays constant. Now, the amplitude of the alternating field is about 6 times the strength of the DC field. So you could say that the DC field is a little bit like, it's kind of set into the background. It's not quite as loud as the voltage from the alternating field. Okay, so now let's discuss the way in which the alternating voltages can affect ion trajectories. Now, to keep this simple and build it up a little bit at a time, we're going to first look at this vertical direction. Let's consider the rods that have only the alternating voltage. So rather than a positive voltage in a sort of DC sense here, let's consider the movement of some ions in this quadrupole region under the influence of these voltages that are oscillating. These voltages are basically going up and down like a sine wave. Sometimes they're positive, then a little while later it flips, they're negative. Positive electric field, negative, positive, negative, etc., changing in time. Now let's think about what these ions are doing. Let's think about how their trajectories are influenced. Any time that the voltage is positive, the ions will be repelled by the rod. And anytime the voltage on the rod is negative, the ions will be attracted to it. So what happens to ions as they go down here with this voltage that's going back and forth? Actually, the times that the voltage is positive is not necessarily a problem for the ions in terms of whether or not they make it through the other end. They would just be repelled. But it would be a problem for the ions the times when these voltages are negative, and the ions would be attracted to the rods, and if they are able to actually accelerate enough that they are able to hit the rods, they're just going to crash there, and they will never make it through. So whether or not an ion actually makes it through this situation where there's an RF field only depends upon the charge of the ion. If the charge on the ion is large, okay, there's strong forces on it, and it will accelerate quickly, and that would increase its chance of smashing into the rod when it does have a negative voltage. Ion mass also factors into the physics of the motion. If the ion mass is, say, low, if it's a light ion, okay, it's going to accelerate quickly, and that too is going to increase the probability that it's going to smash into the rod when the rod is negative. What else is another factor? Okay, the strength of the field is an important factor. The stronger the field, the more likely it is that the ion's going to smash into it when it's negative again. Also, the frequency at which the field flips back and forth from positive to negative, etc., is also another factor. If the field flips back too quickly, the ion will never really be affected that much. Okay? The ion just won't have time to react if it's flipping too quickly, if the frequency of oscillation in that voltage is too high. So now let's look at the combination of DC, direct constant voltage, and alternating voltage on the ion. So in red here I've got the DC voltage, what it's doing. So it's this constant, while the alternating voltage goes up and down as is on the last slide. Okay, so let's look at these ions. Okay, the background DC voltage will tend to keep the ions in there, right? Where the alternating voltage has the potential, no pun intended, to destabilize. So the DC voltage would focus the ions, tend to keep the ions in the center, because the DC voltage is positive, and that it would be repelled by both and sort of trapped in the center. The alternating voltage would have the possibility of destabilizing them. So if the ions are not really affected by the alternating RF fields, either because the charges are too low, the mass is too high, or the fields are fluctuating too quickly, they will tend not to be affected that much by the RF field, and they will be controlled largely by the background field, the background DC field, which has the effect of stabilizing their trajectory. High mass ions will have stable trajectories, but if the mass of the ion is too low, lower than some critical value of mass-charge ratio, the ions will crash. So if the DC voltage is positive, it only lets through ions of high mass. Now I know this is kind of complicated. I had to think about this for quite a while, quite a number of times. I had to go over this before I think I really started to understand it. So watch this video a couple times over, and then maybe look at some other materials. If you really are serious about figuring out the quadrupole, you got to believe that you can, and it will eventually completely come to you. Okay, so anyway, now let's look at the situation where the rods have a negative DC voltage. When the rods have this negative DC voltage, that tends to destabilize the trajectories. The ions would crash. The ions would crash if they were not affected sufficiently by the alternating voltage. So in this situation, the alternating voltage has the chance to save them from crashing. But ions will only be saved if their mass is low. If their masses are low, and they can respond in time. Ions of mass-charge ratio higher than some critical value will crash. And the critical value of mass-charge ratio that does make it through will depend upon variables like the frequency of oscillation, the amplitude of oscillation, the magnitude of the voltages, etc. To summarize, the quadrupole is actually a double mass filter. You've got these two pairs of rods, orthogonal directions at 90 degrees to each other. So we can talk about the way it works quite nicely with a graph. It looks like this, which talks about passage of ions here on the vertical axis. It's basically talking about like whether the ions don't pass or do pass. It's kind of like a binary thing, 0 or 1. So we're talking about whether or not the ions make it through as a function of their mass-charge ratio. So in the y dimension, to summarize, which has a positive DC voltage on those rods, the ions make it through unless their mass is too low. This is a little depiction of what the filter function is like for those y-dimension electrodes. high like this means that they do pass. Low means that they don't pass. Have some critical value of mass charge ratio above which it will make it through, but below that it won't. You have the second dimension, and in the x dimension, which carries on the rods a negative DC voltage, ions traveling down through the quadrupole will make it through unless their mass is too high, as we described. Okay, so the filtering function for that x dimension would look like this. Okay, ions make it through up to a certain critical point in mass charge ratio. Anything above that, ions do not make it through. So here's how the quadrupole is a double mass filter. At certain values of the DC and alternating RF voltages, only a narrow range of mass charge ratios will make it through. Like this narrow range, this is like a little window that will make it through. If you're below, they will be cut off by this filter. If they're above this window, they'll be cut off by the other filter. And so only a little window makes it through. And of course, what we want to do with the quadrupole mass filter is create a mass spectrum which detects ions of all different mass charge ratios and also sort of quantifies how many ions of each type there are. So we want to be able to scan through the entire mass charge ratio range from low to high. And we want to do this ideally pretty quickly so that we can do low to high scans over a bunch of times and then maybe do something like ensemble averaging to add those scans together. But anyway, so that is the reason why I showed you previously, the voltages sort of scanning from low to high over the course of a scan. Okay, thanks for watching, and I hope this has given you some conceptual idea of the way a quadrupole mass filter works.